Hello everyone, my name is Lu, and today I will present a data-driven framework developed for analyze and develop the energy efficiency in industrial melting processes. First, I will introduce the background and the motivation behind this work, and then go through the methodology we used, and then present the case study and the results, and discussion and conclusion in the end. Let's start with the background. The industry sector is responsible for about 40% of global energy consumption, and within industry, the basic metals production accounts for about 25% of the total industrial energy use, which is the most energy-intensive subsector. If we look specifically at the metal casting, the melting stage is a primary energy user, which used for 55% of total process energy. So the melting process is really an energy-intensive activity. So our goal becomes clear. We need to reduce the energy use in the melting process without cutting production output. But how can we achieve our goal? Can we lower the furnace temperature to save the energy? The answer is no, because the metal will not fully melt if the temperature is not enough. Then can we turn off the furnace between melts? The answer is still no, because restarting requires reheating of lining and coil, which cause higher total energy use and production delays. So we can't ignore the physics or production constraints. We need to find a smarter way to use the same energy but more effectively. We're still facing some challenges while improving the energy efficiency. Traditional improvements like upgrading the materials and the design of furnaces require hardware changes, which are really expensive and inflexible. And these physical modifications also don't address the actual operation behavior, which also has a strong impact on the performance of a furnace. Since the melting is operated in cycles, identifying and understanding melting patterns are essential. But most studies depends only on single signal data, which means relationships among multiple process variables. And dynamic behaviors such as feeding and tapping phases are often overlooked. Also, the decision support tools are missed. So our objective is to develop a unified data-driven framework to understand and improve energy efficiency in industrial melting operations. The framework aims to detect complete melting patterns using multi-sensor process data, and the framework will capture key features from each full melting cycle. And then it will evaluate and rank performance patterns based on comprehensive criteria. And finally, it will provide actionable insights for energy-efficient furnace operations. The framework structured in 4 steps. The first step is to identify individual melting cycles from multi-sensor signals, and the second step is to extract performance descriptors from those cycles, and the third step is to cluster similar operations based on the performance descriptors, and the final step is to rank the resulting patterns to find the best practice. Before identifying the melting cycles, we need to select the most suitable signal. So we did the correlation analysis by using Pearson correlation coefficient, which is used to measure the relationship between two process variables. The correlation analysis identifies how strongly different signals are related, and it helps choose a signal that best reflects the core operational behavior. And it also provides a robust and reliable foundation for segmentation across different industrial conditions. After identifying the individual melting cycle, we used k-means clustering to group similar melting cycles based on key performance features. We used two key performance indicators. The first one is the melting rate, which indicates how fast the furnace can melt the material. And the second one is energy specific. It indicates how much energy will be used to melt 1 ton of the metal. And we set the number of the cluster to be 5, because we want to get 4 clusters that can reflect the typical combinations of melting rate and energy specific. And the 5th cluster is to identify outlier patterns. Finally, we will use multi-criteria decision-making to rank and evaluate the clusters. The multi-criteria decision-making can improve the overall decision robustness, and it also helps identify the best performing operational clusters, not just the extreme cases. And we applied 3 multi-criteria decision-making methods, and the criteria were given equal weights to avoid bias. And finally, the ranking will provide the selection of energy-efficient operations. The case we use to validate our framework is a Danish foundry, and the figure shows a production overview. And the data we used is from the induction furnace 8. The figure on the left side shows a 3-time series signal from furnace, and the energy shows the clearest separation between cycles. And the results of the correlation analysis also shows a strong relationship among those variables. So we selected the energy as a primary signal to detect the melting cycle, and we also use weight signal as a secondary check to ensure the reliability. And the flowchart on the right side shows the details of the identification of the melting cycle transition point. And this is a results that shows an example of the unidentified melting processes in one day, and it shows there are 16 complete melting cycles. There are in total over 3,000 complete processes in 16 months. And the left the left figure shows a result of the process clustering based on these 2 key performance indicators. And the cluster 4 is the outlier cluster. And the table on the right side shows the details of those 5 clusters. The upper table shows 6 operational parameters of the 4 main clusters, and the lower table shows the results of the ranking after by using the multi-criteria decision making that across 2 KPIs and the 6 operational parameters. And we can see that the cluster 1 is always the best one. So from the original operations, if we want to melt over 35,000 tons of the metal, we need to use over 17 gigawatt hour over 220 days. But if we only operated the furnace as a cluster 1 patterns, the energy consumption will drop to 15.88 gigawatt hours, which indicate 9.3% energy saving. And the number of melting cycles also will reduce by 5.9%. And the total process time also shortens to 156 days, which indicates a 29% time reduction. So our framework provides a reliable method for detecting melting processes from real production data, and it also demonstrated potential energy savings and reduced the process time. It is also scalable data-driven for decision support, but the framework still have some limitations. The selection of the value of the cluster was chosen for either interpretation, not for statistical accuracy. And the validation was also performed on one furnace. The results may be different in other industrial settings. And the current framework focuses on operational efficiency, and it doesn't integrate other facts like the environmental impact. So to make our framework stronger, in the future we might investigate alternative clustering methods to capture complex operational patterns, and we will also validate the framework across multiple foundries with different technologies, operators, and control systems. And we can also integrate additional performance criteria such as casting quality, CO2 emissions, and economic impacts for more comprehensive assessment. And that's all about my presentation. Thank you for your listening.